Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today what we're going to do is an Inrush Current test, okay? And I'm going to kind of talk about the right and the wrong way. I've actually seen this done wrong, like way too often, okay? And a lot of times it's just not understanding the test equipment and how to get this test done right. It seems like a fairly simple, straightforward, and it kind of is, but you know, unless you run into one of these stumbling blocks, okay? So, for instance, the first way we're going to test this is we're going to hook this guy up into this B&K Precision Power Supply. It's got an isolation transformer, this Variac, and we're going to power up this Jean Hiraga Power Supply. It's the Le Monster. It's got 80,000 microfarads of capacitance and big old bridge rectifiers. So we're going to power this guy up and watch the Inrush Current. When we hit that power switch over here for this power supply, that's kind of strung together here, we're going to have this big Inrush Current, okay? Well, this guy's a 300 VA, so it actually has some impedance. So we're not going to get, that's one of the things that's wrong is testing with the power source that has too much impedance. Alright, so then you can say, well, I'm going to set this up and then I'm going to hit the on switch and that should work. But like I said, the impedance in that. So then, alright, so then you go out and pick out a 3000 VA power supply and you go, this guy has enough oomph, it'll do it. It might, but chances are, and especially if it's a really nice power supply, like let's say if you, even like this is a DC power supply, but you set it all up and then you hit this on or output on switch, okay? You know, like a switch like that. What happens a lot of times, the fancier the power supply is, it's going to limit that inrush current. It's going to ramp that current up real fast, maybe in a millisecond. But that's a long time when you're doing inrush currents. You want that thing to just, you want a mechanical connection just to close quick. And you want a low impedance source. So the second way we're going to do this test, we're going to plug it right into the power strip over there and hit the on switch and see the difference, okay? Another thing that you might have is you might have a really expensive power supply, say a $10,000, $20,000 power supply that is all programmable, and you can say turn on a certain phase of the sine wave, and you say, well, I want it to turn on right at the peak, then I'll get my max test. Well, you're like, wow, this power supply is designed for this kind of thing, okay. Well, what happens is you might not get the peak value there. What I found is you have to experiment a little bit depending on your circuit. I found that just before peak of the waveform is actually the max, because things have, it takes time for things to happen, like the say maybe the transformer is going to collapse, the magnetic field is going to start to build and then collapse. Well, if you turn on your power supply right at the peak, it's starting from peak and dropping. So if you start just before peak, it has a time to kind of let that current build up, and then you get your peak at the top, okay? For sure, if you turn it on at zero crossing, like some power supplies are designed to do, that's going to give you the least amount of inrush current. Well, when you're just kind of haphazardly flipping the switch on and off and just hoping by luck you're going to get the waveform, yeah, you know, that's not a bad way to do it, but you're going to have to try it maybe 5 times at least, 10 at least, and maybe up to 20 times, maybe even more, because as you do it, you might see, oh man, I'm catching at the same time every time, and like you're just like, okay, come on, get a better peak this time. So you just have to do it a bunch of times to try to get the peak waveform. So we'll do those two, and we'll stick this thermistor in there and show how a little 10 ohm thermistor, relatively inexpensive thermistor, can give you predicted results, okay? This guy starts off 10 ohms. At max current, he'll heat up and drop down to 0.1 ohms. So that's how we're going to do it in this power supply. So yeah, this is for the Class A amplifier, the Aleph 5. Okay, and so as part of this test, what I want to do is I want to take the Hantek and compare it to the Micsig. I got the Hantek first, and it was like, I think 65 bucks, but you can often find it for, I think, less than 60. And then I got this Micsig. Micsig gave me this one to review. That was super nice. That was like $460, I think, list price. I see it on sale, I think, for under $250. That's still a lot of money. Now, this guy has a 2.5 megahertz bandwidth. This is a CP2100B. The A is the little brother of this guy, and he goes to 800 kilohertz, I think. And his prices, he lists for about half the price. So you can find him, I think, under 200 bucks. So I'll put links to both these guys, but I'm going to test these guys side by side on the scope here on this Micsig, and you'll be able to see what the waveforms look like. Do they give the same peak value? Do they give the same shape? Or do they distort the waveform? We'll find out. And then the other thing is I want to take this little, this was also given to me, this little Kaiwit. This is like a $22 meter. Now, a lot of these clamp-ons, they have this max button where they'll capture the max current. Some of the more expensive guys will capture peak inrush current. And but we'll see. Like, often you'll use a clamp-on meter like this to capture inrush to, say, a water pump motor, or just any kind of motor as it spins up. It has an inrush current. Fans, up to 200-300 milliseconds sometimes, though. It takes them to spin up to full speed, and meanwhile they're really taking a lot of current until they get full speed, and then they're kind of idling. Okay, not idling, but then they're in gear and they're coasting. Anyway, the run speed takes less current than the startup current. Okay, and these guys, so we're going to see what this guy looks like compared to those two. All right, and they're still useful. Okay, now this kind of stuff happens really quick compared to motors and fans, but still can be useful. So we'll look at that too. All right, okay, so let me show you the whiteboard, and we're going to go over some stuff, and then we'll jump into testing. Okay, hopefully I don't have a glare on this thing. Okay, just ignore all this stuff for just a moment here. This is my simplified schematic. The inrush current's coming in, right? We've got our fuse, our switch, transformer, bridge rectifier, and these guys are our output caps, and this signifies the 4 volt capacitors on the one rail, the 40,000 microfarads. This is the other 40,000. Okay, so that's kind of our DC power supply here. And I'm showing the 2 windings in parallel. That's why I kind of drew it that way. In the US, 120 volt, 60 cycle. So, if you're in other parts of the world, you'd put those in series. So anyway, that's why I drew it, okay? All right, so let's just talk. When you close that switch, current's going to build up a magnetic field here. It's going to, through turns ratio, put the voltage over here. The voltage is going to start coming up, and as it does, it's going to try to charge these caps. Those caps are going to look like a short circuit. So in essence, what that does is it makes it look like it's short over here. So this current coming in just looks like it's short until these guys start to charge. That's how you start off, okay? Into a short circuit, basically. Okay, so let's just talk about that. Current is going to be equal to our voltage in divided by the resistance, Ohm's law, and that's what your peak current's going to be. But the resistance of this kind of thing is a little bit complex, and I can go through this in another video if you guys are interested in doing that. We'll do the KISS method. but for now, we'll do the super KISS method. We can just say that between here and the capacitors, it's going to be some real small ohms. Say if it was 1 ohm. If you had 120 volts RMS coming in, you'd have a 120 amps. That's a lot of current. And it's not unheard of. I mean, you can see that kind of current. You're going to have some impedance with the transformer. Now, initially, the transformer is going to have enough current that's probably going to be saturating. So it's going to take a few cycles to charge up these caps, and then the waveforms will start looking more natural here. Okay, so let's just talk about how caps charge. There's this capacitor charge formula that looks like this. Okay, you take the peak current, whatever your peak current's going to be, say it's at 120 amps, and then you multiply that by the natural log of minus t over tau. And tau is just the RC, time constant. And I show tau, not to be fancy or anything, but you might see the equation shown that way. And just so it's common to you, it's not, you don't misunderstand it, tau just means RC, as TAU, the Greek letter. So you take the T over the tau, and you calculate this, and what you do is, let's just say your time constant, they call it a constant because once you get your R and once you get your C, it's just a constant number. Now in reality, something especially like this, the R is going to be changing, okay? But let's just say it's constant. Like in a DC system, it's a lot easier to do that. AC, it's a little trickier, but we can look at the extreme ends and kind of, you know, figure it out. Once you get RC, let's just say that's a millisecond. So when you say T, okay, when T is equal to 1 millisecond after I close that switch, then 1 millisecond divided by the 1 millisecond time constant is -1. And that's my first time constant. And when the time is 5 times my RC constant, that's the 5 time constants. Okay, so you might have heard about this. Usually the first 5 time constants, your capacitor's charged up. Now, if this comes out at 10 milliseconds, then it's just 10 times longer. Each one of these times are just, you know, it's changes. But what this is showing is T equals 0, I'm just saying right here, instead of drawing it at the origin right here. So it's kind of like that stopwatch. We're going to start the race right now, and it happened to be right here, not there. So 1 millisecond later, that's our first time constant, and the current's going to drop 63% of its peak value at that point. Okay, and then it's going to drop down to 86% the second time constant, and down here to the fifth, it's 99% of its final value. Okay, these last 3 time constants are going from 95 to 99, so it's only changing a little bit at that point. The biggest changes are those first 2 time constants. So whatever your RC equation turns out to be, you know, 2 times that, you're 86% charge or discharge. Well, you're 86 voltage charge, and the current has dropped down 86%. So by the way, if we're applying the voltage, it'd be this equation, and all it is 1 minus this E. So I just changed the current to voltage, and the equation, and so what the graph would look like is start here and it'd pop up to 63% of its final value, then 86%, and then 99% of its final value as it charges. Okay, that's what it would look like if you turn on a switch and had a fixed voltage, a fixed resistance, and a fixed RC. That's what it looked like. AC, it's going to look different. We're going to have 60 cycles of current. And in a case like this, it's going to be 120 cycles by the time we go over here, right? Because we double that, because we take all the negative pulses and put them up towards a positive, or vice versa. On the negative row, we do the opposite. But you get 120 pulses on each one of these caps. But each pulse is about 8.3 milliseconds long. So depending on where we happen to hit the switch on that waveform is going to depend on how much current we see on that first inrush. Okay, and so a lot of times you have to, it's common to try this, if you're doing this method, to hit it 20 times, and you'll start to see after first few times, you'll start to see as a common value, and then you'll kind of be able to tell from the look of the waveform where you're getting lucky or unlucky when you hit that switch, and you keep on trying until you get some real high peak values. Okay, you just have to discharge your caps in between each try. So let's just go ahead and get testing and see what we can find. Alright, let's just go over the setup, okay? Here's the power supply, you know, the rectifiers, and these are all 10 millifarad capacitors, and they have some output fuses, and I'm measuring the voltage out here. And these 2 meters here are measuring voltage. This is a plus V and that's the minus V. And then I'm using this resistor to discharge the capacitor bank so I can get to the next test cell quicker. And we're going to start off with this AC power supply from, let me lift it up so you can see it. It's a B&K Dynascan 1653 AC power supply. This thing was made in the US some years ago. I've had that for quite a while. So we're going to start off with that, okay? And we're going to take some measurements, and we're going to compare the Micsig current probe to the Hantek. Now, they're connected to the same thing. One's just on the you know, it's the AC power cycling through. So one's on the input side, one's on the output. So they're seeing the same current. Okay, I just wanted to separate them so the field that's generated, if there is any field that's, you know, they're not coupling to each other or any interference that way. And then, you know, I got this little Kiwitz HT200B probe in here. So I thought, just for fun, we'll see what that does for capturing max values, okay? So after this view, what I'm going to do is I'm going to zoom in so you can see the scope and the meters, okay? And then I'll just come here, hit this power switch on, and then I'll discharge and we'll do several tests. All right, so let's do that. Okay guys, we've got the voltage turned up to about 120 volts, and I'm going to set this guy to max reading, and this guy's single sequence, and channel 2 is the Micsig right here in the middle, and the Hantek is channel 3 right below it. So they're set at 10 amps per division right now, and both probes are set at the 100x position because I'm expecting to see some high current. So it's going to be above 10 amps anyway, and they're next set. So the 10x scale is 10 amps, and so they're both set at their higher scale. Okay. Now you can also see the voltages are discharged down to under half a volt. All right, so I think we're ready to go. Let's do it. All right, there we go. And you can see it charged up to just over 37 volts. I turn it on, turn it right off, so they're kind of discharging right now, as you see. But look at this. This thing caught 3.8 amps. Now, this is 10 amps per scale, so that's about 15 amps peak. I've got the measurement set, so that says 14.96, and this guy's 15.15. You can see how closely the wave shapes look like each other. You know, if I moved channel 3 right up on top of channel 2, I mean, they are very hard to tell the difference. So it looks like the Hantek has done a good job. Alright, so that was the first one, but yeah, our peak was only around 15 amps. I would expect to see a lot higher than that. But see where the switch got turned on is right, you know, if you look at where the waveform is, it was right after the peak of the negative as it's coming up. So the voltage wasn't at its peak value there, I don't think. It was already around the bottom curving up. Okay, so let's try it again. I'll reset this to max. And we'll have to discharge the output caps. So now they're discharged under a volt. We're going to put single sequence and we're going to try again. Okay, here we go. Well, we got up over 38 volts, and our peak, again, it's about the same. Just under 15 amps here and 15 and a half amps on the Hantek. So they are pretty darn close. And even the shape of them, see how the shape, now look where we turned on. We turned on almost at the 0 crossing. So yeah, we're not getting a big inrush right there. We're getting kind of lucky, or unlucky, whichever way you look at it. All right, I've reset everything. We're under a half volt over here. Kiwitz is ready to go. Let's do it again. All right, that might have been closer to a peak, but still, we're not getting that high of peak currents, right? It's under 20 amps. Still, we're 15.8 here roughly, 15.56. So this time, the Hantek and the Micsig are very close. And look, this guy, when he goes over 3 amps, he turns orange, saying that, you know, kind of warning you. 3.4 amps. So you're saying that's nowhere near the peak. But this guy measures, I think it's probably around 100 milliseconds, and then it takes an RMS of that. So each cycle is about 16, 17 milliseconds. So it's taking several cycles and taking the RMS value of that. All right, let's try it one more time. All right, everything's all set to go. I'm going to hit the switch and see what we catch. Hopefully at top of a waveform. Well, it's hard to say. It looks like we got pretty much a full cycle here, so I think I got it right as we're crossing 0. So yeah, we're just not getting a real high peak. By the way, the FLIR has a flashing warning sign because the voltage is above 32 volts or whatever. So it thinks we got some dangerous voltage over there. And the Kaiweets thinks we got some dangerous current. Alright guys, so we're going to try this one last time, and then I'm going to explain something. We're going to move on. Alright, single sequence set. We're all ready to go. Let's do it. It's hard to tell. It seems like every time I switch it on, it's right. We see a full, half cycle. It seems like. All right, but still, we should see a lot higher current than this, and it just seems like we're not getting this high peak. Well, this B&K power supply down here that I showed you, this AC power supply, it has a transformer and stuff. There's some impedance. It's only, I think it's a 300 VA power supply, so it doesn't have a lot of oomph. Okay, we're testing things that are looking pretty good, so I'm going to go straight to the mains, a power strip. It has a circuit breaker in it, but I'm going to go right to there so we can get less impedance in our power source. Okay, our power's plugged into the power strip over here, so we're going to come straight from our power source. I expect to see something higher. Everything's all reset. Let's go ahead and do it. Wow, went right off the screen. First time. And look where I hit it. Is the waveform is just ending on one, so might not have been at a peak either, right? And also look at these funky looking waveforms. So I think that what that is our transformer saturating, guys, and collapses. Okay, but look at this peak, went right off. So we need to drop our amplitude. I mean, we need to get our scale at 20 amps so we can capture it. 52.7, 62.5. The waveforms, the shape of them looks very similar. That's an important thing. Not just the amplitude, but actual shape, to show that they have the same kind of, that the Hantek can be just as fast at capturing a good waveform. Okay, so it looks good. Let's do it again. Okay, I got everything set up, ready to go. Let's go ahead and turn it on. Wow, that's pretty strange looking. 39 amps, 39.3. I mean, they are tracking very well. But yeah, it's hard to say where I got it turned on, and we're saturating the transformer. But yeah, we're getting 39 amps. We're getting quite a few more amps than we were when we were going through the B&K power supply, right? Okay, we'll do this one last time, see if we can capture a real high spike. All right, looks like we're ready to go. Let's do it. Man, that looked like an, oh, you know what? It looked like it triggered off the page somewhere. Huh. All right. Not sure why that did that. I'm going to move the trigger over one notch just to, well, a couple. We won't capture as many cycles this way. You know what I can do is, let's change our scale. That way we can capture more cycles. So if it, for some reason, pre-triggers, we'll capture that, okay? Alright, this one's going to be the magic. Let's see. Okay, that looks like a pretty interesting peak. Now this is 20 amps per. We're getting, well, we're still around 31 amps on each one. Alright guys, let's put this thermistor in line. And this guy here is a 10 ohm thermistor. So let's see what he does. Okay guys, let's check the ohms on the amp probe here, and I'll just go across this thermistor. Alright, it's around 13 ohms. It's kind of cool in my lab, so it's around 13 ohms. Let's see what happens. Okay, we're all set to go, but you know what? I'm going to change this to 10 amps because I have a feeling we're going to be much more, well, you know what? I'm going to go with 5 amps on each one. And I don't think we're going to go off screen. I think we're going to look good. So let's go ahead, and you can see the thermistor right here. It's just in series right there with the transformer. Alright, let's do it. Alright, so now we're at 8.9 amps and 8.6 amps. See how much more controlled it is? instead of having these big peaks and dropping down, each cycle is getting a fair amount of current, but much less than what it was. So that's what our thermistor does for us. Look at this, 3 amps RMS. So it's just barely over the 3. All right, I hear you. Let's do it one more time to make sure. Okay, here we go. We're all set, ready to go. Looks pretty darn near the same waveform, right? 9.54, 9.4. So if you think about that, we have 120 volts coming in. Let's just say we had a 10 ohm. That'd be 12 amps. And it was about 12 or 13 amps, so it's just right about what we'd expect, right? So it's very, you know, with the thermistor, it makes it very easy to calculate what your peak currents are going to be, and you know, no surprises. Hey guys, so what do you think? Okay, so I want to cover a couple things. One thing is when you're trying to get an inrush current measurement off a power supply and you're turning the switch on and off, or if you're doing a DC one, you have a power supply here where you can hit the output on off, that doesn't give you an inrush current, okay? A lot of times these power supplies are regulated so they can only put out so much current per second, you know, so they have a ramp that they control things to protect themselves, and also they think they're protecting the circuit that they're powering, so they have a controlled turn on. So to do an inrush test, you need a switch like that, or I have a big old knife switch that I might have shown you in an earlier video. I haven't used it yet, but I have a big old knife switch that you just shut down. Especially if you have 3-phase power, you can use breaker switches. That's, you know, kind of a common thing. A lot of guys use a breaker switch to engage the switch. But yeah, you need some hard metal contact, and you don't want to be pulling power for your power supply. Yes, this one's a small one, but even if you have a big one, there's going to be some impedance. And again, you don't know the electronics inside is slowing down that inrush. So you want to go right to, if you're doing AC power inrush, you want to go right to the line power, okay? Right where you're going to plug in when the thing's going to be in use. All right, so that's one thing, is to do the inrush, you need to do it correctly. The other thing is that Hantek did a great job. It hung right in there with the Micsig waveforms. I mean, they're so close to measurements. I didn't zero the meters every time, so that could account for some difference too. They're close enough. I thought, wow, the fact that the wave shapes looked so similar, that one wasn't smoothed off, or you know, it wasn't able to capture the detail. You know, the Hantek caught the same detail that the Micsig did, so that's pretty cool. Now, getting to the Kaiweets, I put that in there just to kind of show you what it was doing, just to kind of make a point. A lot of the meters, the bench meters or the current clamp-on meters, I think when you do that max measurement, they're all going to be similar. They're going to be around 100 milliseconds that they're going to capture and sample that, and they may only take 5 samples in that 100 milliseconds, so they're not even capturing, you know, the peaks maybe, but they're going to capture so many samples during probably 100 milliseconds and give you an RMS value of that. All right, that's a lot of the ways that they're set up, and one of the reasons that kind of makes sense is because circuit breakers, they don't operate, even fuses, they don't operate, you know, instantly. There's some time. There's a IT curve, okay, and so it's an I squared T curve, and it has to do with how much current versus time, and it takes depending on how much over you are the rating, say a 15 amp breaker, you have to be over that 15 amps for some time for them to pop. And when you pick out breakers, you can get ones that have inrush control, but even if they don't, they're still slow. And I think 100 milliseconds is kind of a standard thing that a lot of fans, when they kick on, it takes so many cycles for them to spin up. And it's usually, I think, more like 200 or 300 milliseconds before they spin up. So if it's capturing the first 100 milliseconds, it's capturing the worst of that. And I just wanted to point that out. That's why I put that into the test, just so, you know, just make that point. just kind of throw it out there. A little extra learning thing. Well guys, hope you liked it. Thumbs up. Again, that helps the video. YouTube algorithms, that really does. Appreciate it. And thanks to the Patreons. Really appreciate all your support and everybody for watching the videos. And you can become a patron for as little as $1 a month. Throw that out there. Is there anything else I missed? Seemed like there's one more thing I was going to point out. Okay, oh, that thermistor, by the way, you know, for low cost part, I mean, that's really cool how you can control the peak current. You don't saturate things, you don't stress all your parts. It's not real critical, the ohm value. You know, I mean, I was almost going to say fudge factor. I mean, you just pick one, you know, that's like say 10 ohms, 12, 15 ohms, because as like I am in here, it's kind of cool in this lab. So that's a 10 amp guy, but it was up to 13 ohms. So, you know, a tolerance that, who knows, but even if you just say at 10 ohms, if you looked at the curve, you could probably tell how cool it is in this lab. So when they get hot, you know, once that inrush current comes through and you get a steady flow of current, that ohms on that guy, it drops down to, I forget what it is right now. It's under a half an ohm, I believe. And the warmer they get, the lower they drop. But yeah, I've shown that thermistor in other videos before. I need to look that spec. I'll put it down at the bottom what the range is, okay? But yeah, they're easy to use, and you just have to get one that can handle the energy, and there you go. Alright guys, hey, thanks for watching. We'll see you next time.